this is lecture 11, and here we look at another version of Nullstellensatz. This is the more classical version. So this is a classical version of Nullstellensatz. And proved by Hilbert. Okay, so the theorem, so again, the notation is R is polynomial ring in n variables over a field K algebraically closed. Then the ideal of the variety of the ideal of I is the radical of I. So let's prove this. Again, we will prove it assuming the versions, the equivalent versions that we proved in the last lecture. I mean, assuming the two versions that we saw in the last lecture, which we proved were equivalent to each other, but we didn't prove that either of them were true. So assuming that statement, we will prove this. And as I mentioned, we will prove the version 2, the description of maximal ideals, after we develop some more algebra. So let proof. Let f be an element of the ideal of the variety of I. So let me just remind you what this is. Given any variety, we can look at, given any I, we can look at its variety, and then we can ask what are all the polynomials which vanish on that V of I. Okay, so maybe I should just, to remind ourselves, we should say what this is. So this is G in R such that G of A equals 0 for all A in V of I. Okay. And we want to show that, so we want to show that there exists an M such that f to the M is inside I. Okay. Yeah. So this is the proof of the statement is a clever trick done as follows. Okay. So let F1 through Fm be a generating set of I. Okay. So what we want to show is that f to the m, sorry, not the same, let's call this some other symbol. Okay. So what we want to show is that f to the m is in this ideal, the ideal generated by these elements. Okay. So we define a new ring S, which is the same variables x, n of them, and a new variable y. In that, we define a new ideal in S defined by F1 through Fr, the generators of I, and a new element which is 1 minus y times f. So f is a polynomial just in the x's. So we're writing a polynomial like this. Okay, so now the observation that we want to make, okay, is that V of j is empty. Okay, so let's look at why that is the case. So you should write out the details. It's not very difficult. So if a point, if B is an n plus 1 tuple which is in V of j, then these polynomials vanish. By definition of f, f vanishes, but then 1 minus yf cannot vanish. Okay, so that's, okay, so check this detail. So we have J is empty, which means that J is S. So this is what we call the weak Nullstellensatz. Okay. So in other words, 1 belongs to J. So we can write 1 in terms of these elements. Okay. Therefore, there exist S1 through SR inside S and some S inside S such that 1 equals S1 F1 plus SR FR plus S times 1 minus YF. That's just saying 1 is in the ideal generated by F1 through FR and 1 plus YF. The coefficients have to come from S. Okay. So now so this is all part of the trick. Okay. So the next is we consider a ring map. So there exists a ring map which goes from S to some large ring. Okay. We can make it more precise after we develop some things, but it's not relevant for the proof. The ring that we will consider is the rational function field in the x variables. Okay. So there exists a ring map in which k elements of k go to the same elements here. Xi also goes to xi and yi goes to 1 over f. Okay. So now let's apply, so let's call this thing star. Okay. Apply, so and let's call this map phi. Okay. Let's apply phi to star, this equation here. Okay. So phi is a ring homomorphism, phi of 1 is 1. Okay. Fi is just Fi, Fi involves only the x's and xi is mapped to xi's, so that is just Fi. Okay. But on the other hand, what does Si go to? Si goes to, so Si is a polynomial in n plus 1 variables, the x's and y becomes 1 over f. Okay. Fi is unchanged, and so this is the first term, the first part. So these terms, this is what it becomes, and S goes to whatever it is. 1 minus YF becomes 0. That's exactly why this was written like this. Okay. Plus 0. Okay. So this is because phi of 1 minus YF is 0. Okay. That's the. Okay. So now we got an expression about 1, not involving polynomials, but one also needs to allow for rational functions which have an f in the denominator. Okay. So this is not exactly an expression in the ring R, but it is an expression in the rational function field in the same variables. The only observation you have to make is the denominator will only involve powers of f. It will not involve other polynomials. Okay. So because of this, we can clear denominators. So what does S1 of, so Si of x1 through xn 1 over f will look like some polynomial, some gi of x1 through xn. Remember, fn also involves only x's. So okay, when we write this out and then in the expression of the polynomial, clear denominators, and then we will get some f to some mi. Okay. So that gives us for some gi and mi greater than or equal to 0. gi is just a polynomial. So we can write it like this. So now multiply by a large enough power of multiply by f to the n for some for sufficiently large n. Okay. That would clear all the denominators of which have f's, the powers of f in the denominator, and then we would get some f to the n is some elements of gi, and however many f's were multiplied to times fi. Okay. So this is in the ideal generated by f1 through fn, fr, which was I. Okay. So this is the proof. Okay. So this is just it's just a clever trick. So what it does is it passes to a larger ring, and where after a substitution we can introduce f's in the denominator and then clear the denominators, one would get an expression like this. So this is what we wanted to prove. Okay. So based on this, so from what we have seen so far, it is now sort of clear that the radical of an ideal is an important object associated with an ideal. So we can ask, so we saw in the last lecture how to test for memberships in ideals. So now we can ask whether we can test for membership in ideals, and so this is called radical membership test. Okay. Notice that if f is in radical of I, if and only if f is in I of v of I. This is what we just proved, that radical of I is equal to this. Okay. So if f is in radical of I, then there is a point, if f is in the radical of I, then now let's consider, so I is this f1 through fr, okay. J is the ideal generated by f1 through fr and 1 minus yf. So this is inside R, ideal of R, this is an ideal of S. Same notation as in the theorem. Okay. Now if f belongs to this, equivalently if f belongs to this ideal would be the unit ideal. If f does not vanish at some point where the fi's vanish, then this has a solution. So let's check, let me write down what I just said. Okay. So if f vanishes everywhere where the fi's vanish, then f is in the radical. Okay. So that we can write from the previous theorem, that f is in the radical implies that f of a is 0 for all a in v of I. Okay. So if you substitute for any one of, if you substitute a point where the fi's vanish, then f will also vanish, and hence this does not have any solution. So this means that J is the unit ideal. Okay. Let's think about the converse. If J is the unit ideal, then let's do it the other way around. Suppose f is not in the radical. So suppose f is not in the radical. This implies that there exists some a inside v of I where f of a is not 0. This is where the other direction of f is not in the radical means f is not in I of v of I. So there is such a point. Okay. So we get this, and from this what can we conclude? If you substitute a to these polynomials, these things vanish, so that's okay. and f does not vanish, then appropriately you can choose a y such that 1 minus fy vanishes. So then set y to be 1 over f of a, then 1 minus yf vanishes, I mean this value of y vanishes at a1 through an, and this value of f of a. Okay, and this is well defined because it is non-zero. Okay, so in other words, j is not equal to s. So the question whether whether f is inside the radical of I is precisely determined by whether j is s or not, and then we know that the test, therefore the test is f is in the radical of I if and only if 1 is in the Grosvenor basis of I, Grosvenor basis of j in some order. Notice that in these discussions we don't need to decide, the discussion does not have an underlying, one need not worry about an underlying order, but to use this theorem once we have to set an order, compute the Grosvenor basis in any order, not some, in any order, in any monomial order. Okay. So this is the radical membership test. Okay. F is inside I is same thing as j being equal to s, which is same thing as 1 being inside j, and one can immediately write this in terms of a Grosvenor basis. Okay, so now we want to sort of study some more about Grosvenor basis, and in fact how do we compute a Grosvenor basis given a generating set. So typically when we write a program, it would be one would write down the generating set, and then one would need to know the Grosvenor basis, and so this is called Buchberger algorithm. Okay. So I'll quickly discuss two examples of this, although we never learned it as examples of this. Okay. And the Buchberger algorithm cleverly puts these things together and proceeds. Okay. So the first example is Gaussian elimination. Of solving linear equations. So let's say we have two polynomials, x plus y plus z equals 1. So I'll write it as x plus y plus z minus 1 equals 0. Okay, and let's mark the leading terms. Well, we don't know about leading terms when you do Gaussian elimination, but we knew we get rid of the x and so on. We'll write it in a matrix and do row reduction, but I'm just writing the same thing in polynomials, just to see that this is what we were doing. Okay, let's say the other polynomial is 2x plus z minus 3 equals 0. Okay, whose leading term is this. Okay, so we would like to simplify these leading terms, just for convenience, we would like to make them all units, all 1. So let's rewrite this as x plus half z minus 3 halves is 0. Okay, and the leading term doesn't change. Okay, so now these two, the first and the third equation, have the same leading term. Take the difference. Okay, so that when you take the difference, of first and third. Okay. So that would give us y plus half z plus half equals 0, for which this is the leading term. Okay. So now if you go back how this was done in matrices, we would say there are two pivot variables x and y, different ones, and this is all that Gaussian elimination can do. So we will now solve for y, we'll set arbitrary values to z and solve for y, then together in this equation, and then we'll go back to this equation and solve for x. Okay. So that's how Gaussian elimination, or we could use these two equations, give arbitrary values to z and then solve for y from here and solve for x from there. Okay, so this is what we did in Gaussian elimination. Okay. Now example 2. Is polynomials in one variable. So earlier we looked, the linear thing is many variables but linear equations. Now polynomials but in one variable. Okay. So let's take some example. Let's say that f is x squared, x cube plus 7x plus 1, and g is x squared minus 1. We want to know if they have a common 0. Okay. Does there exist a point a in k such that f of a equals 0 equals g of a? Okay. That's what we would like to answer. And so we would do division algorithm here. So we would write division algorithm as f as x times g plus 8x plus 1. So the first round of division algorithm gives this remainder. Okay. So then if f of a is 0 and g of a is 0, then for this also it would be 0. So let's call this thing h of x. Okay. So f of a equals 0 equals g of a would imply that h of a is also 0. Now we will do between h and g. Okay. And this is a little complicated expression, so let me just copy what I've already worked out. 1/8 x minus 1/64 times hx plus 1/64. Okay. So this is what we have. So now, so this is g. Okay. So if g of a is 0 and h of a is 0, then 1/64 is 0. This is a contradiction. Okay. So what does that say? It says that the system is inconsistent. Okay. We would like, so what Buchberger algorithm does is to put these ideas together and do for multivariate polynomials of arbitrary degree, not linear polynomials. Okay. So we need an important notion on how these things are cancelled. So it has to do with, so let's look over here. How were the leading terms cancelled? The coefficients were adjusted and then subtracted. Here, how was it done? Well, the leading terms were adjusted by multiplying by monomials. So here it was some x times g, and then we cancel the leading term. And here, so I suppressed 2 steps. It was really 1/8 x times h, and then some leftover was there which was adjusted through this. So I suppressed 2 steps inside here. But even here, this can be broken into 2 steps in which monomials were multiplying the the divisor and then cancelling with the polynomial from which we were dividing. Okay. So we would like to capture this thing properly. So this is an important definition in this study of Grosvenor basis. Let f, so maybe I should, so hereafter R is k x1 through xn. No assumption on k, it's a field, but no assumption that it is algebraically closed or not. Any field is fine. Okay. Definition. Let f and g be two polynomials in R non-zero. Okay. The S pair, so I must apologize, I do not know why it's called a pair. It's a single sorry, let me finish that. S pair, or sometimes called, I think also called a polynomial of f and g is, okay, there is some monomial order. We are discussing Grosvenor basis, so there is some order that is being used. Okay, that's begun. Yes. Okay. So let me write it here. We take the initial term of f, the initial term of g, take their LCM, divide by the initial term of f, and multiply by f. Okay. So now this multiplies f. Similarly, we do the same thing for g also. You take the LCM of the initial term of f, initial term of g, divided by the initial term of g, multiply by g. Now, if we notice, both of these things have the same initial term, which is the LCM. Okay, which is why precisely we took the LCM divided by initial term multiplied by f. Okay, would just make, first of all, this is a monomial, and you multiply that monomial to f, the initial term will get multiplied by this monomial. Okay, so they both have the same leading term, and the difference is what is called it's called written SFG. Okay, so this is sometimes called the S pair, although it is not clear why it's called a pair, but many books, and Macaulay also uses S pair, and sometimes some books refer to it as S polynomial. So we'll interchangeably use both ourselves. Okay, sorry, this is what. So this is what is S pair is. Okay, so this is the key idea behind cancelling leading terms. Multiply appropriately and then subtract. Okay. We did this in many of the examples yesterday. Not yesterday, in one of the previous lectures. Sorry, not in the previous lecture. Okay, so now this is the key result of Buchberger, which we will prove in the next lecture. Okay, so for now we will just state it and use it as you describe an algorithm. Okay. Let G inside I be a generating set. Okay. Then G is a Grosvenor basis of I if and only if the following condition holds. So this is a, sorry, I should have said it's a finite, let me just fix this thing a little bit. Let me actually label, it's a finite set, and let me write them as G1 through Gn. for all, if and only if, for all pairs I different from j. Okay. So now we can apply the division algorithm on the S. We can first compute SGI SGJ, sorry, SGI GJ. Okay. We can apply the division algorithm by elements of G, okay, in any order we want. Okay. So the remainder of, sorry, let me just, it's badly positioned, let me just write it here. For all I different from j, okay, and the remainder of S of gi gj, the S, so we take the, we appropriately multiply ga and gj and take the difference to cancel the leading term. So we take this. Si gi gj. The remainder of this for division by G in any order, in any order of elements of G, okay, is 0. Okay, so we can apply the division algorithm and run the division algorithm on this remainder by elements of G in some order, and it doesn't matter which order you choose. If the remainder is 0, then this is true for every pairs I and j, then G is a Grosvenor basis. Okay. So this is what, sorry, this is slightly more longer to write than actually to say what it is. We take S pairs for arbitrary ij, I different from j, and then we just run the division algorithm by the elements of G in some order, independent of the order. The remainder should be 0. Okay. So we will we'll quickly describe the Buchberger algorithm to compute Grosvenor basis, which is based on that theorem. Okay. So what is given? Given some F1 to Fr inside R, okay, and what we want is, and given and a monomial order is greater than symbol, want a Grosvenor basis of the ideal generated by F1 through Fr. Okay. So we start, okay. So start with G as the set. Okay. And we repeatedly ask the following, do the following computation. For F different from G inside G, both of them inside G, compute the remainder of SFG, okay, call the remainder H. Okay. If H is 0, nothing to be done this step. Okay. Just do for another pair. Okay, so repeat for another pair. Okay. And if H is non-zero, replace G by throw in H also into the collection. Okay, and now again do this and stop when the remainder is 0 for every pair. Remainder division by compute the remainder of SFG. Sorry, I should have said this here. Here, for division by G. Okay. So compute the remainder for 1, and then we just check. So the remainder will have terms, none of which is divisible by in G, in of an element inside the set G. So then throw that. If it is non-zero, then throw that also. This enlarges G. If it is 0, there is nothing to do. Repeat this. At some stage, this will stop. Okay. So why? This will stop because it gives an ascending chain. As you add more and more elements to G, the ideal generated by G grows up a little bit, but eventually it has to stop. Okay. So this is the algorithm, and this is the most basic elementary algorithm to compute Grosvenor basis. Many of the programs have various improvements over these things. We will not discuss those things. We just want to have one conceptual understanding of how Grosvenor basis is computed. Okay, so we will prove this theorem in the next lecture, which is that this is the crucial property of Grosvenor basis, that a generating set is a Grosvenor basis precisely when the S polynomial between pairs reduce to 0 when you divide by elements of G.